Okay, so hello everyone, and welcome to part 2 of the overview session of Spartan-ECDSA with Daniel Tehrani from Personae Lab. Shout out to those of you who have been poking around, running tests, asking questions. That's great. This week is all about this. It's all about tinkering around and throwing as many questions as you want. So so that hopefully you make sense of what we have in scope. So on Friday, we're going to have one of your fellows, actually, Pratyush, who's going to come speak about Plonkish arithmetization. And we may have another speaker coming to talk about MSM next week, which is very relevant to today's audit, to this week's audit, I mean. In Discord, if you guys are working within a group and you would like to have your own private channel, let me know and I'll create it for you. And with that, I will pass the mic to Daniel. Daniel, welcome, and the mic is yours.
Thank you. So let me just share my screen. And then first of all, it was great seeing people actually poking around the circuits, running tests, and actually finding some issues already. So thank you for working on it, and I got some good questions. So that assisted me to design this session. And for this session, I decided to just go over Poseidon as planned, and take the time to take any questions regarding this session's topic, Poseidon, or any other questions regarding the code base or efficient ECDSA or any SECP arithmetic things. So just to quickly recap what we did in session 1, I first explained the motivation behind Spartan-ECDSA, why we built it, and some techniques, some core components used in Spartan-ECDSA, and explained the scope of this audit, and went through some actual algorithms and constraints written in the library. For this session, I'm going to explain Poseidon, which is used in the Merkle tree, which is used in the Merkle proof. So the Merkle tree is based on the Poseidon hash function. And Spartan-ECDSA implements Poseidon in Circom and Rust. And the scope of the audit only consists of the Circom implementation, but I believe the Rust implementation will also be useful in auditing, because it is usually easier to read Rust code than to read Circom constraints. So first of all, if you have any questions, feel free to interrupt and ask anytime. You can also ask in the chat. Please let me know if there's anything in the chat, or you can just say it out loud. And all right, so to start off, I want to explain the background of why we had to implement our own Poseidon implementation in Circom and Rust, rather than simply using the implementation in Circom lib. The reason is that we need to use a Poseidon instance that works over the base field of the SECP curve. Poseidon is a algebraic hash function, so it operates on finite field elements. So we need the Poseidon hash function that operates on the SECP base field elements. And circumlib doesn't provide that. It only provides Poseidon for some usually called ZK friendly curves like BN256, and I think also probably also other curves, but it didn't provide the SECP base field instance, so we had to implement our own Poseidon. And more precisely, we needed to generate the constants used in the hash function that works over our base field. And the constants, the generation of constants depends on the finite field order. So it's finite field dependent. So we needed to generate our own constants and use those constants. So that's the main parts that differ, that is unique to our Poseidon instance. And yeah, as I said earlier, we implemented Poseidon SecP in Circum and Rust, and the Circum implementation is in the scope of this audit. I believe the Rust implementation will be also used for in auditing, and there are tests written in Rust. So if you want to run the Poseidon written in Rust, you can go to the there's a link to the directory, so you can run this test and see the output and see if it matches the output of the Circum implementation. Right. And the Poseidon implementation is inspired by Filecoin's specification. They implement their own Poseidon instance called Neptune, which is, I believe, used in Filecoin. And there is a specification of Neptune that we followed to implement our Poseidon SecP. And I think the specification will also be really useful when poking around these circuits. So as I said earlier, the unique part of our Poseidon instance is that the constants used in the hash function. And I'll go through the actual hash function and what's actually done inside hash function a little later. But I just want to share how we generated the constants. There is a Sage script from the official. It might not be official, but it's linked in the official Poseidon website. This Sage script, does it load? Yes, pretty big. So there's a Sage script to generate the constants depending on your parameters, like the security level and the finite field that you're using. So we just plugged in our parameters and then ran this Sage code and generated our constants. And you probably need to install Sage to your local device to run this script. But that could be a little tedious, so I just pasted the output of the script ran with the input or Poseidon instance in the hackmd. So if you want to refer to the output, you can just go to the hackmd and then copy paste this thing. And there is also a security inequality check defined in the Filecoin spec. So if the constants are, there is a set of inequalities that check if the constants and the inputs to generate the constants are safe. So we there wasn't any Sage script to check the inequalities. There was just this mentioned in the Neptune spec, Filecoin spec. So we just set up a simple script to check all of these inequalities to check our parameters are safe. And this Sage script is in the repo, and it's a lot smaller than the script to generate the constants. So you can actually run it in SageMath Cell, which is a website you can run Sage scripts online, and just to run it right now. Yeah, so if you wanted to check, you can go to the this website and paste the script and run the script. And yeah, these are the parameters that we use, and we see that all of the inequalities are satisfied. So this is just a useful reference to check that the parameters are safe and how we check the parameters are safe. Right. So that's the that's the overview. And to go into the actual Poseidon implementation and what's done inside, let me share my VS Code. Question is a reason to have chosen limits. Yeah, so good question. I believe there are other implementations and other spec as well, but it seemed like the Neptune specification was the most detailed, and it was actually battle tested and audited. So I think it's one of the most robust, if not the most robust implementation out there. So yeah, that's why we chose Neptune. Right. Yeah. So I will just quickly go over the actual hash function and what is done inside. But I believe this might be, I believe with just this explanation, it might be hard to grasp what's happening. So I recommend going to the Neptune specification and also just reading the code yourself and after this session. But I just wanted to provide some context and provide some hints, hoping that will be helpful. So first of all, hash functions operate on has a state in a state, and then it modifies and mutates the state according to the input, using a constants and using other polynomials. So we have the state in the Poseidon instance, which has 3 field elements. And this is our this number of field elements. So the size of the state could depend on the Poseidon instance, but we use a state with size 3 because the only use case of Poseidon for us is to hash leaves in the Merkle tree. So a Merkle tree uses Poseidon to hash two elements into one. So that's why we have with the domain tag that needs to be added to the first element. With that plus the 2 inputs, we'll have 3 field elements in our state. And with this state, we will mutate. With this starting point, we will mutate the state using the constants and using a thing called S boxes. They are. Go ahead.
So Daniel, input 0 and input 1, these are 2 leaves, and then domain tag is the root, the hash root of the 2.
The domain tag is just an input to distinguish hash outputs between applications, but I mean between different number of inputs. So this domain tag 3 is defined in the Neptune specification. So the Neptune spec specifies the domain tag to be the 2 to the power of the RT. So in our case 2, because we have 2 leaves, minus 1, so it's 3. So if you have like 4, if you want to have a 4 input Poseidon, that will be 2 to the power of 4 minus 1, 15. But in our case, it's just 3. So this is just a predefined tag, and it's static. And The hash function consists of various rounds, and there are two types of rounds called full rounds and partial rounds. And the number of full rounds, so how many times we run the full rounds, is determined by the security level, and the partial round is the same thing. And we first run half of our full rounds. So if we have 10 full rounds, we'll run 5 first and run all partial rounds, and then run the last 5 full rounds. And the output is just the first element in the state index, indexing from 0. So the hash output, the actual hash, is just a single field element. So diving into the actual rounds, explaining from the full round. First, we take our state. So for the very first round, the state will be the main tag and our inputs. We take that, and then first we add the constants to the state, and the constants are the thing that is generated by the Sage script that I explained earlier. The constants are, let's see. Yeah, it's just like these things. So we just add some predefined constants to our state in the full round. In the first step of our full round, our state has 3 field elements. So first we add the first 3 constants to our field element, and then proceed to the next step, which is applying the S boxes. And the S boxes are simply a function that takes in a field element and outputs some power of that field element. In our case, we output, or we set the exponent to be 5. So we simply take our state field element and take the power of 5, and then set and update the state to be that output. In other instances, like various security levels, this power might be 3 or other numbers, but usually it's in our instance, and usually in I guess in fields that are used often, it's usually 5. So this is the part we apply the S boxes. And the next is to do a matrix multiplication. We take our state, which is in our case, it's a vector of dimension 3, and we have our MDX matrix. Where is it? Right, so our matrix is just a 3 by 3 matrix. So with our vector and our matrix, the vector matrix multiplication will result in another vector with 3 elements. So we simply multiply our state by this matrix, and then set the state to be the result of the multiplication. So yeah, so that's the step that we do after applying the X boxes matrix multiplication, and then that's the entire full round. We just update the position, so we can use the next set of constants in our next round. But the main parts are these 3 steps: add some constants to our state, apply S boxes, and do a matrix multiplication. So that's the full round. And the partial round is almost the same as the full round, but the only difference is that we apply the S box to only to the first element. So in the full round, we apply to all of the elements in the state, but in the partial round, we only apply to the first element. So with that, with adding a bunch of constants, applying S boxes and doing a bunch of matrix multiplication, we result in a pseudorandom hash, and then the hash is the first elements of the mutated state. Okay, so this is the implementation in Rust. So if you're familiar with Rust, this could be pretty. This shouldn't be that. I believe it will be a lot easier to read than to read circum constraints. But the Poseidon.circum, this implements the exact same thing as our Rust implementation, and it outputs the same hash, and the constants are obviously the same. Right. So yeah, so that's all I have to explain about Poseidon. So if you have any questions, let me know. Also, also if you have any questions about about the circuits or about Sekpi arithmetic or the things that I talked about in the last session, feel free to ask about that as well in this session.
Yeah, thanks, Daniel. Yeah, the floor is open for you guys if you have any questions, either about Poseidon itself, what Daniel just talked about, or in general.
Oh, I probably should have sent. Just send in the Zoom chat. So the spec of Neptune, so the spec of Poseidon, is linked in the HackMD. I can also just sent a link in the chat. So if you want to take a look.
What kind of testing, Daniel, would you recommend fellows to do in terms of maybe fuzzing the two implementations, the Rust and Circom, for example, like pipelining the two and asserting the equality between the two or something like that? Have you yourself done like any testing in general?
Yes. So I'm not sure if there are unit tests to test if the two outputs equal, but let's see. Poseidon test. There are no fuzzing tests, so that might be a valuable test to do. There is a Poseidon.test.ts, which like directly encodes the output of the output from the Rust implementation and check if that equals the output of the circuit. So that's like the most basic and simplest test. But yeah, in general, because we use the Rust implementation when generating proofs. So when you want to get the Merkle proof to provide as input to your circuit, you need to generate the Merkle proof on your device. So you need to have some implementation to run the Poseidon in the browser and in the command line. command line. So we use Rust. We actually use WASM by compiling the Rust implementation, Rust Poseidon implementation to WASM, and run that WASM in a browser to compute the miracle proof. And we haven't seen any any issues in terms of outputs. We haven't seen any different outputs from the same input between the two implementations. So there are, yeah, in general, it should be the two implementations should be equivalent. So I think it might, but still, I think fuzz test will be nice.
Okay, well, let's make this a little bit fun, and I'll tell the fellows we will issue a bounty. So you guys can work on the best testing utility, basically. How I would do it maybe is to create a batch script that runs, fuzzes the two and asserts equality in some way. So let's make this some fun, and by the end of this audit sprint, we will hand out bounties to the best testing utility, basically. And testing actually is something we learned in this fellowship that is lacking in testing SDKs for CIRCOM code bases. So this is maybe a low-hanging fruit for you guys to create tools that could be very useful for everyone. So yeah, consider the bounty issued. I won't say how much, but let's just say it's a nice bounty. Plus, we will add you to the contributors of the fellowship generally. So that should be fun. Igor was asking if there are other implementations of Neptune.
I don't know anything other than the actual Neptune implementation, the original one.
Okay. So I guess the link you have here, Lurk Lab. Is this an official implementation, Igor? Lurk Lab implementation?
I believe so, yes.
Okay. Igor is also following up with the question about the curves, the curve that Filecoin is using.
Okay. Yes, Filecoin is using, I think it says in the README, yeah, it uses the BLOS 12381 curve.
Is the
And
Poseidon spec
yeah.
itself recommend, does it recommend a specific curve, the standard spec of Poseidon?
I don't think so. It mentions various curves that might be interesting or that might that might get an option, but I don't think it recommends any curves. The security parameters, the security inequality, so checking the security of a particular instance, there is a universal inequalities to check them, so it should work with any finite fields.
I noticed, Daniel, in the Rust code, you're using usize. Is there a risk there that the usize might be larger than the curve order, maybe, or something?
Let me see.
Is that checked somewhere?
Usize. I think usize is only used for indexing, like counting rounds and indexing the constant positions. So we use for the actual field element. So the field element, we use these. Yeah, there is a sec Q256K1 package in the repo as well. So we define field operations in that Rust crate and use that use a struct in there to emulate the field. So there shouldn't be any issues with, like, around overflows.
Okay, any more question, guys? One fun thing that I was going to recommend to Daniel today or tomorrow when you have time is to probably post 3 questions, one easy, one medium, one hard. And then the fellows will use these questions to determine how much they understand the code base. So we're not going to post any answers to the 3 of them. I have been trying to come up with questions, but I think you, Daniel, will come up with much better questions. So we will be posting these 3 questions, and you guys can use them as a, as an indication of how well you understand the code base. So if you maybe understand the easy question this week and then the medium and hard by next week, that means you're doing well. So
Yeah, sounds good.
Okay, yeah, awesome. So if you're working on these, as I said, if you work on the testing utility or working on something else and you want to organize an ad hoc session, just you guys, feel free to do so. You can invite others as well. This week is about, there are no stupid questions, just, it's about throwing everything against the wall so you can understand and dig around. So don't be shy, basically. So I think we covered everything. So unless there are any more questions, I'll give 5 more seconds. Go ahead, Parsley.
I watched some videos on Poseidon and M3S, and one of the things they did to make it faster was kind of only use the left half of the information when they did the hashing. Do you do something similar?
Yeah, great question. So there is a optimized version of Neptune. So in the Neptune spec, there is the basic implementation of Poseidon, and there is an optimized implementation of Poseidon. But for now, we just implement the standard one, so the basic one. So we don't do any kind of optimizations. But I believe Neptune has a bunch of optimizations, and yeah, where a lot of hashing anywhere, any like projects regarding a lot of hashing, I think they have a bunch of optimization, but our Poseidon is just a basic implementation, so should be relatively simpler to understand.
Thank you.
Any more questions before we wrap up?
Yeah, on the studying resources, I think the actual Neptune spec is the best one if you want to read more about how Poseidon works. It might be a little bit lengthy at first, but it shouldn't be that. It doesn't do, yeah, it might be a little lengthy, but I think it is readable. And yeah, I believe that's the best resource to read. So I do recommend that one.
Okay. Well, thank you so much, Daniel. Thank you, everyone. And we will see you on Discord.
Thank you.